just a reminder again, Thursday, yes. Okay, I might mix up the dates, okay, but I already anyways, we'll just continue with the discussion on metal, and the test will be on microscopic worldwide. Okay, book 1B, the entire book 1B. Okay, so we discussed some uses of metal, some properties of like metal, general properties of metals, and then we also look at some special uses, okay, of metal. For example, okay, so in here we look at a select few metals and their applications. Okay, so you may want to put this down on the notebook. So and their applications. So starting with iron. So what is the symbol of iron? Fe. Okay, yeah. So we have iron, Fe. So it is relatively cheap. Okay, and this is the second most abundant metal. Okay, that you should know. What do you think is the most abundant metal in the earth? Do you know which metal is the most abundant? Metal is somewhere in this classroom. It's aluminium. Okay, aluminium. So aluminium is the most abundant metal. Iron follows it. Iron is the second most abundant metal. So can you put down some properties of these select few metals? Okay, so we have iron, which is number one. You can put down second most abundant. Right, so second most abundant metal, which partly explains why it is used in so many different applications. The second feature of iron is that it's fairly strong, especially when it is turned into what we call steel. So all of you should have heard of steel, right? We use steel to make cutlery. We use steel to make the frame of the car body. Yeah, so steel is an alloy made from iron. Okay, so it's fairly strong, and it is made even stronger when turned into the alloy steel. So when turned into the alloy known as steel. So if you don't know what the difference is between pure iron and steel, draw this diagram. Okay, so this is pure iron. What pure iron looks like in a microscopic scale, and on the right is what steel looks like on a microscopic scale. So you can first draw a bunch of circles here, each representing an iron atom. So, and you tell me what you notice when you compare the structure of steel and pure iron. So in steel, you notice some carbon atoms, okay, like on top of the iron atoms in here, you see. So these are, you can put down iron atoms. The term, so the term pure iron means there is only iron atoms found inside the structure, no other thing. That's what pure means. And steel is a mixture, okay, of iron atoms and some carbon atoms. So the carbon atoms disrupt the otherwise ordered arrangement of iron. So you see before I add the carbon, the iron can stack on one another very easily, okay, very efficiently. And that will allow smooth sliding of layers. So there's not a problem sliding one layer across the other when you have pure iron, but not so much with steel. So for steel, like the layers of atoms simply cannot slide past one another easily. So this explains the hardness, okay, of steel compared to pure iron. So can you put them against one another and write down what you find from the structure? So easy sliding of layers on the left. Yeah, so carbon atoms that disrupt the orderly arrangement that prevents the sliding. Think of the carbon atoms as something like a door wedge. You know, you put the door wedge under the door just to prevent the door from sliding smoothly, right? That's exactly what the carbon atoms are doing. So you can write down they are acting like a door wedge. Well, and the door here will be the iron atoms, okay? You don't want them to slide past one another easily. So sliding is difficult. So sliding, because it's difficult, it is harder to deform, which explains why it's stronger. So in many applications like cutlery, you don't want the knife to bend before your stick. You know, it should be the stick that gets cut into half, not your like a cutting knife, right? So in those instances, you want to use stainless steel, which is pretty strong, okay? So it won't bend easily. So it is harder and stronger. This is why we often use steel, okay, in the making of a lot of tools, okay, instead of pure iron. So that's iron, and we have, so you can put down a few things made from iron. For example, we have like so cutlery. So cutlery is made from steel. Okay, you know, reinforced concrete. What does reinforced concrete mean? You are putting some steel rods in concrete. Have you seen people like building like stuff at a construction site? They don't just pour concrete. Concrete is not strong enough to support the weight of the building. They need to put a lot of bits of steel rods inside. So therefore, you have reinforced concrete. They are reinforcing the concrete with steel. That's what the term reinforced means. Okay. So reinforced concrete basically means concrete with steel rods. Okay, and most importantly, you will also use like a steel in the buildings of bridges and also the making of car body. Okay, you want the car body to protect the passenger inside. So that's iron. We will also look at aluminum. Aluminum is also a pretty popular metal. Okay, anyone knows the special property of aluminum? Oh, and before that, okay, can you put down a weakness of iron? It is that it will rust. Okay, it will rust when exposed to air, to the oxygen and water in air. So therefore, put down a big, like a dot in here, and write down iron is susceptible, meaning vulnerable, okay, to rusting. So it's susceptible to rusting. In the presence of something, of course, it doesn't rust by itself, but as we learn in Form 1, okay, it only rusts in the presence of oxygen and water. Okay, so you can write the word equation now, okay, and that is iron plus oxygen plus water forms rust. Yeah, rust is a brown substance. Okay, and it is weak. So therefore, when iron one rusts, it becomes weaker and it breaks easily. So structures, when they rust, they don't tend to last for very long. Okay, from that point on. So therefore, we don't want bridges to rust. We'll do some things to prevent rusting, as you will learn later. But then, the next metal I want to draw your attention to. So again, I think we should write down these properties of iron first. And then we will look at aluminium. So what's the symbol of aluminium? Al. Yeah, Al. Okay. So but any question about iron first? No. Okay. Okay. So the most abundant metal is aluminium. Okay. But then aluminium wasn't used until very late, like in history. Do you know why? Why is it that there's so much more aluminium in the earth crust, but then we use iron earlier than we use aluminium?
It's easier to extract iron.
Yes, it's easier to extract iron because of its lower reactivity, as you see. So this is what a lot of students might have in mind, this question. Why is aluminium so abundant, much more abundant than iron, but yet it is used much later in time? Well, first of all, this is the most abundant metal, yeah, more so than iron. But yeah, so what limit is used then? So question, this is a question they will ask, probably ask. Okay, so what limits is used? Yeah, and why is it that so it is widely used much later than iron? Okay, so much later than iron. Well, that's because, so the answer here now, okay, because iron is less reactive, which makes it easier to extract. Okay, so which makes it easier to extract. You know why in this lesson. So which makes it easier to extract, yeah, from its ore. I hope you remember the term ore. So what are ores? So ores are rock that contain a particular type of metal. Okay, so this is from these rocks that we extract metals. So you do not expect to find a block of aluminium lying on the floor, okay, in nature. So metals are not found like that. So metals are found trapped inside an ore. Okay, so you need to do something to pull the metal out from the ore, to extract them. Okay, so that's called metal extraction. So easier to extract than aluminium. Okay, so there was a time when the peasants, they would serve gold dishes. I mean, on a gold, like food, they serve on a gold plate. Okay, but then the you know, the nobles, okay, they were served aluminium plates because there was a time when aluminium was even more expensive than gold. Okay, so you can look that up. Yeah, the peasants were served food on a gold plate, and the noble people didn't have the aluminium plate because aluminium is more expensive at some point in time. But now, of course, aluminium is cheaper than gold. Okay, this is because gold is pretty rare metal. So, and can you put down some unique properties of aluminium? Okay, it is light yet strong. So it is light yet strong, which explains it's used in some applications where lightness is very important, like planes, okay, aeroplanes. So it is light yet strong. Okay, so it makes its way into, you know, the overhead power cables. So sometimes when you go hiking, you see things like these. Okay, the cables hanging from between two towers. Okay, so those overhead power cables, they are made from aluminium. Okay, because if they were made from other metal, other heavy metals, they would droop. Okay, and when there's strong wind, typhoon or something, they break easily. So we want these overhead power cables to be as light as possible. So we made it from a light but strong metal, aluminium. And the second application, which I'm sure all of you will understand, is in planes. Yeah, the aircraft body is made mostly of aluminium. Okay, because the luggages, the passengers, they are heavy enough. Okay, you want to, you know, keep the aircraft body light. Okay, so that you can fly more easily the jet. So we will only be discussing these two particular metals here, or maybe just one more. Is copper. So just one more metal in here, copper. So copper has symbol Cu. Okay, remember the second letter, if it is present, is always in lowercase. Okay, just like in here Al, the L is in lowercase. So copper, what's so special about it? It is known for its high electrical and heat conductivity. So those of you who also do physics, you will know. It has very high heat and electrical conductivity. So though it has not as high and electrical conductivity as gold. Okay, yes.
Does aluminium have any weaknesses?
Has a
Weaknesses? Any weaknesses?
any weaknesses? Well, its only weakness is when it's come into contact with mercury. So can you see what happens when we put aluminium? This is why you're not allowed to bring a mercury thermometer on the flight. And this is a block of aluminium.
Some weighs up, right?
Yeah,
Like a ton of comes out.
Yeah, until it comes out and it will just eat its way through the aluminum. So imagine what happens if you're on the plane and you just drop a thermometer with mercury inside and it slips into the fuselage of the plane. This is what happens to the plane. And disintegrate in the air. Okay, so therefore, if you're wondering why would a thermometer containing mercury not be allowed, like this is why. So therefore, to answer your question, maybe the weakness of aluminum is mercury. So mercury is its natural energy. Okay, so they don't combine, they don't play nice together. Okay, so mercury and gallium. So both of these metals, you see, they have this tendency to, dissolve the aluminum. Yeah, but other than this, aluminum is pretty strong. Okay, so can you put down one extra property of aluminum I forgot to mention? So note, unlike iron, when aluminum is exposed to oxygen, it is made stronger. Remember, iron, when it's exposed to oxygen, is made weaker, right? It forms rust. Aluminum is the opposite. When it is exposed to oxygen, it is made stronger. Why is that? When aluminum is exposed to oxygen, it grows stronger. Why? So this is because the aluminum, when it is exposed, it will form a layer of oxide. So can you tell me what's the formula of the oxide of aluminum? Knowing that aluminum is in group 3, oxygen is in group 6. Can you do crisscross rule and tell me, first of all, you need to figure out the charge from the group number. Al is group 3, O is group 6. Then you do crisscross rule and combine those ion charges together. So what is the formula of aluminum oxide? What is the charge of something from group 3? Well, this will be on the test, I tell you. Okay, what is Al2O? One more number is needed. So Al is group 3, so it will form a 3 plus charge ion. Oxygen is group 6, so it will form a -2 ion. So what does it mean to do crisscross rule? Al2O3. Well, you better revise because there are a few questions. Okay, say on this on the test. Okay, and usually put it away. Okay, so you need to know that. So this oxide, what's so special about it? It is impervious. Yeah, meaning impenetrable. Okay, to oxygen and water. So it blocks oxygen from reacting further. Okay, so therefore it protects it. So you can draw this. So you have aluminum here. Once the surface becomes exposed to oxygen, it forms this thin layer of aluminum oxide. So but don't underestimate this thin layer. This layer of aluminum oxide is said to be impervious. So impervious means impenetrable. Okay. So this is impervious. Okay, to oxygen and water. So these substances, they can no longer attack the aluminum inside. So they are blocked out. Okay, so the aluminum oxide, although it's a very thin layer that surrounds this aluminum metal, it blocks the oxygen from going in, from reacting with the aluminum inside. So it keeps aluminum out. Okay, so this is the complete opposite of iron. When iron rusts, it peels off, it forms rust, it grows weaker. When aluminum is exposed to oxygen, it doesn't rust. So know that the term rust is specific to iron. Only iron rusts. No other metals rust. Okay, you can however say that all other metals can, some other metals can react with oxygen, like in here, aluminum. So can you write down the oxygen reacts with Al to form Al2O3, which protects it. So protects it how? By being impervious, okay, to oxygen and water. Okay, so this is not a weakness, but more like a strength of aluminum. And the only, I would say, disadvantage to using aluminum is its price in extraction. Okay, you need to use very expensive electricity to extract it from its ore. Okay, from its ore. So that's the only downside to using other than that, it's light or strong. It is the most abundant metal. It is tough. Okay, even tougher when it goes to oxygen. Okay, really great metal. Which is why you see aluminum being used in so many applications. Window frame, laptops, you name it. Okay, yeah, plane body, you name it. So we have copper next. Okay, and then we will turn to the metal reactivity. So copper is known for its very high heat and electrical conductivity. So you can do an experiment if you have two different metal plates at home. So this is copper strip. Let's say you also have some zinc strip or maybe iron strip at home. Having iron is pretty easy to come by. Okay, so you may buy two metal strips at home. And to do a fair scientific experiment, we want to use two strips of the same dimensions. Okay, yeah, I know I don't draw them to be of the same size, but let me try it. Okay, so you have two different strips. To test the conductivity of these two metals, you can use some wax. Okay, so what you need is just a paper clip or any object that carries weight. You attach a paper clip to one end of both of these metals using wax that has solidified. Well, first you need to melt the wax, stick the clip in it, and then you let it solidify. So the clip will now be suspended, okay, on the strip. What do you do next? You hold a candle near the other end of the strip. You just put it there. And do you know what will happen?
The more conductive one will melt the wax first.
Yes, okay, so the wax will melt because heat, you see heat can be conducted, okay, from one end of the metal to the other. And what is so special about copper again? Okay, right here, very high heat and electrical conductivity. So heat is spread more quickly to the other side of the metal than in iron. So you see in iron, heat is also transferred but more slowly. So therefore you will see this paper clip fall down first. Okay, so this is how we see in action the higher heat conductivity of copper. Is that clear? So can you put down the experimental outcome? So the paper clip will, so this paper clip will fall down first, and it tells you something. So you know in science, in scientific experiment we draw a conclusion. So the conclusion is that heat is conducted through the metal, copper, more quickly than in iron. This is why the wax melts first, and so it releases the paper clip first. Okay? So it's conducted through copper faster than in iron. So therefore wax melts first. Yeah, so wax on the left melts first, and the paper clip falls down. Okay, and the clip falls. Is that clear? So that's how we test the heat conductivity. What about electrical conductivity? How do you test the electrical conductivity of a substance? Yeah, circuit. We actually have discussed this some time ago. Not sure if you remember. Let me just refresh your memory. This one. We can use this circuit here, okay, to test the conductivity of a substance. The more conductive the substance, the brighter the bulb glows. If it is not conductive at all, it will not glow at all. Okay, so from the brightness of the bulb, we can tell if something is conductive or like or not. Okay, so I'm not going to paste this on your notebook. But you should remember this from before. So just paste this in here. So on the top right, what is this a test of? This is a test of heat conductivity. It's a test of heat conductivity. So 1 second. So test of heat conductivity. And over here on this side, we have a test of electrical conductivity. They're not the same, obviously. like you see in so you see in electronic appliances, like the laptop, the tablet, the television. Okay, there are circuit boards. On the circuit board, you see those contacts in gold color, but it's actually not gold because we have to use gold in all electronic appliances. We'll run out of gold pretty soon. So those contacts are made from copper. Yeah. So therefore, can you put down some applications? So I ran out of space here, so we can right now. It is used in the electronic appliances as copper wires. Yeah, even in sockets. Yeah, even in sockets, you see you have a lot of metal wires twisted into like a like a big form of wire. So you have copper wire. You have copper pots at home. You may have copper pots at home. So these like pots made from copper, they conduct heat very quickly. Okay, so therefore you can use it to boil water very quickly. So that's a few uses of a few important metals. So now we should know something about iron, copper, and aluminum. So the next thing we'll turn to is their reactivity. Unfortunately, not all metals are created equal. Some are more reactive than the other. And as such, we have something called the metal reactivity. By the way, this is not the first time we discussed that. Remember the mnemonic for memorizing the order of reactivity? It's to use a very silly sentence, right? Remember, please stop calling me a QC L. Okay, let me show you where we mentioned that. Like long time ago. It's I think I did, but maybe not on this for some reason. Okay, anyway, I'll just put it in here. So put down the sentence if you don't already remember. Please stop calling me a title first. We call it metal reactivity series. So not all metals are created equal. So not all metals are created equal. And by that, we mean some are more reactive than the others. Okay? So to memorize the order, we have this very interesting mnemonic. So please stop calling me a cute zebra. So the second half sounds weird, sounds off. I like her for smart goat. Well, unless you can come up with a better way. And this is the way we are used for now. So let's translate this back to symbols. Okay? By the way, the letter you see in the first letter you see in each of these words is the first letter in the element. They are not the symbol. So P, therefore, is potassium here. Because I know the symbol of potassium is not P but K, but let me emphasize this again. It is the first letter of the name of the element, not the symbol. So P for potassium now. Okay, so you have P for potassium. S for sodium. The symbol of sodium, however, is Na. So to not confuse yourself, put down the symbol as well. So starting from the third one, I want some volunteers. Okay. So what do you think the third one is? Calcium. So we have calcium. What's the symbol? Ca. Yeah. So from this point onward, can I have some answers? Okay, from the audience. Okay, like both the name and the symbol. So what's the next one?
Magnesium.
Magnesium. Symbol.
Mg.
Mg. Yes. Okay. And then we have, what is the most abundant metal again? Aluminium. With symbol Al. And this is when things get interesting. Can you use a special pen? Maybe a red pen? Yeah. Make this red as well. That's because they are not metals. Yeah. Don't you find this weird? We are talking about metal reactivity series. Why do we have a non-metal in here? Well, later you will see. This non-metal dictates like a how the other metals they are extracted. But put this down first. This is a special element, carbon. This is not a metal, okay, but you will see why we put it inside the metal reactivity series. So let's continue. We have zinc. What's the symbol of zinc? Zn, yeah, Zn. And then we have iron, so I'll just give you the rest. simplest element. So finally, we have copper, silver, and gold. So copper, silver, gold, Cu, Ag, and Au. Okay, so these are the order of metal reactivity. Okay, so and you need to memorize it one way or the other. So like I said, if you find this very silly, this method, so tell me if you got a better way. So you have the most reactive metal on top, the least reactive metal at the bottom. That's what I mean by not all metals are created equal. You have some metals more reactive on top, yeah, and you have some metals that are less reactive at the bottom. So we'll first look at how metals are extracted, okay, by looking at ores. Okay, so just now a lot of you look very confused when I mentioned the word ore. We actually mentioned that some time ago. So put this down if you forgot what it means. So ore, okay, this is where metals originate. So like I always say, you will not stumble upon like a piece of aluminium when you go hiking. It's just not going to happen. Okay, that's because metals that are, especially those high up in reactivity, what does being more reactive mean? It means they will react, combine with other stuff. So this is why when you find aluminum in nature, usually it's combined with other elements. For example, oxygen. So and this is what we mean by ore. So where metal originates. So most metals. So put down most. So most metals are not found in a free state. So free meaning unbonded. So free unbonded state. Yeah, that's because of their reactivity. So because of their reactivity. And by being a reactive metal, they react with other elements in the air. For example, oxygen. Sometimes they can also react with sulfur. Okay, so this means, okay, these metals will react with other elements, such as O or S, okay, to form oxide and sulfide. Okay, so such as O or S to form compounds, okay, like oxide or sulfide. So remember we learned about the naming of compounds, right? Things with oxygen, they are called oxide. Sodium oxide, carbon dioxide. Okay, anything with oxygen in it, we usually call them oxides. And most things with sulfur in it, we call them sulfides. So when metal reacts with oxygen, they form oxide. So write down this equation here. Metal plus oxygen forms metal oxide. Which is all one actually, the aluminium. Remember, aluminium is very stronger, okay, by reacting with oxygen. So aluminium will react with oxygen to form Al2O3. Yeah, but this is not balanced. Okay, I don't want to confuse you, okay, with the numbers. Okay, but if you understand how to balance the equation, then you will know that because we have 2O on the left, 3 O's on the right, the numbers aren't right. We need to do something to fix it. How can we fix the balancing of equation here? We can put 2 in front of well, if you put 2 in here, you will run into a problem. The number of O will still not match when you put a 2 in here. So therefore, we try to turn 2 and 3 into the LCM. What is the LCM of 2 and 3? 6. How do you turn 2 into 6? 3. Multiplying by 3. How do you turn 3 into 6? 2. Multiplying by 2. So once you put a 2 in here, how many AL would there be? If you put a 2 here, 4. So finally you put 4 here. This is why you shouldn't put 2 here first. Because if you put 2 here, you're not going anywhere, as the O is still not balanced. Okay, so put this down 4, 3, and 2. Okay, but because here we are shape in a much later part. Okay, so it has a crown shape. So if you like, you can draw this crown. If you know how to draw a crown, you know how to draw a shape. Yes, crown shape. Okay, so this is what oxygen looks like. And you see, those are double bonds holding two O atoms together, and these are single bonds holding these S atoms together, 8 of them, forming a crown-shaped molecule. So now, I want you all to challenge yourself to balance this equation. So what do we need? Okay, we only need 2 numbers here. Okay, so how can we balance this equation? With the product being 6 sulfide. So to balance the equation means to put some threshold number. We call this mole ratio. How can we balance it? Yeah, we put 8 in front of CNS. And once you put an 8 here, the number of sulfur is balanced. What do we do next? In front of zinc, right? Yeah, so can you put down what these numbers mean? Okay, these are called the mole ratio. They are also known as coefficients. So you know when you learn math, you know a squared plus 2ab plus 2b squared. These numbers in front, we call them coefficients. We also call this coefficient in chemistry. But there's an even better word, mole ratio. Okay, so these are the same coefficients you learn in math. Okay, the numbers before a term, we call those coefficients. So, okay, next up, many metals, okay, they are not found in a free and bound state because of the reactivity. Some metals, though, okay, so this is why I pay attention to some special words, okay, especially when I put a box around those are important words. So some metals, yeah, however, can, okay, exist in the free unbound state because of their unreactivity. You know, 2 of these metals are gold and silver. So because of their, so learn another word for unreactivity today. Inertness. Okay, so inertness means unreactivity. Okay, so unreactivity or inertness. When you say something is inert, you mean they are unreactive. Okay, not even when you throw oxygen at them, will they react? They will not react at all. Yeah, so these metals, they are called noble metals. So these metals are known as noble metals. So you know we have noble gases, right? So noble metals, they are still more reactive than noble gases, okay, but compared to other metals, they are one of a kind. They are very unreactive. So they are called noble metals. Put down 2 examples. Silver and gold. Yeah, so silver normally will not react with oxygen, but it may react with other elements, okay? But gold will simply not react with any other element. So most other elements. So you have gold and silver here. So can you draw a box around this point and then link it back to here? So some metals, only these 2, they are so unreactive. They are very they are found near the bottom end of the reactivity. They are called noble metals. They hardly react. But most metals on top, they will react with either oxygen or sulfur. So therefore, they are not found in the free unbound state. Okay. So these metals on top, excluding the red ones, of course, because the red ones are not metals. Yeah. So you can put down this is about the top metals. Okay, so you can write down also a description in here. These metals, okay, are not found in the free unbound state. Yeah, they are always bound to something. Okay, and these metals are usually found in the unbound state. So are usually found in the free unbound state. So if you have visited what is that? Like I think the museum in Cairo, in Egypt. okay, you will have seen the King Tutankhamun's sarcophagus. You know what that is, right? Yeah. So this one. So. I'm not sure if that's very important against sarcophagus, meaning the coffin, okay? I think I spelled his name wrong anyway, but I think else. So this thing, okay, is known as the sarcophagus. It's basically a tomb in Egyptian terms, okay? It's made of gold, pure gold, okay? So when this is unearthed, it remains in this mint condition, okay? That's because it will not react with oxygen at all. You see most other metals, when they react with oxygen, do they retain their shininess or will they lose their luster upon reacting with oxygen? They will lose their luster. Okay, so this sets gold apart from all those other metals, making a noble metal. Gold will remain in this mint pristine condition, no matter how long it's exposed to oxygen. It will simply not react, okay, with the oxygen. So this is what being like a so unreactive means. Okay, so I'll just put this in here. Yeah, so that you remember. So this is the sarcophagus of King Tutankhamun. Okay, it's made from pure gold. So this is pure gold. Because this is pure gold, and pure gold is very inert or unreactive, therefore it remains shiny no matter how long it's exposed to oxygen. Okay, no matter how long it's exposed. But look at other metals. I think I showed you this video before. Look at the other metals like calcium. So this is calcium. It loses its shininess over time, right? Yeah, and this is not even a time-lapse video, it's in real time. But no matter how long you expose gold to air, this thing will not happen to gold. Yeah, this is known as tarnishing, losing shininess, losing its natural luster. So this is what we will turn to next as well. So we can learn a few things about the metal reactivity, which I want to go down on the opposite side. Things we can learn from the reactivity. So things we can learn from the metal reactivity series. Number one, it's what different metals react with. Okay, so put that number one. Like what different metals can or cannot react with. So can or cannot react with. And number two, we can also use the the metal reactivity to explain, okay, why certain metals they are used first, okay, in human history. Do you know what is the earliest metal used since civilization begins? It's not copper, but gold and silver. Because these two metals, do they need any extraction? No, as they are already in a free, unbonded state. You know what does the term extraction mean? Extraction means to pull the metal from its compound. So if gold and silver don't form compounds at all, do you need any extraction work? No, right? Yeah, so therefore, put down number two. The order in which the metals are discovered, okay, or used since civilization began. Okay, so discover or use. And so these two things really. And number three is how the metal can be extracted. So we can learn three things from the order of reactivity. The first one is what the metal can or cannot react with. The second thing is the order in which they appear in human history. Okay? And finally is how they can be extracted. So we will look at these three now. Okay? So let's look at the first one. What metals can or cannot react with? Okay, so generally speaking, the higher the order of metal in the reactivity, the more reactive it is. So it can react with these things. So number one, reactivity. reactivity, we look at each of these terms in detail now. Okay, so this is just a summary of all, and now we look at term 1 in detail. So reactivity of metals. So metals generally react with the following things. So metals react with, may react with, yeah, I said may because it also depends on the reactivity. Number one, oxygen to form oxide. Okay, so so plus oxygen to form oxide, you have metal oxide. It can also react with water to form oxide or hydroxide. So metal hydroxide. Do you remember hydroxide? This may appear in the test. Hydroxide is one of the, is it monoatomic or polyatomic ion? Polyatomic. Anyone remember the formula? Wow, you better revise. Okay, it's a good thing we don't have the test today. So it's OH minus. Where was it? Where was it? I think it's almost. Oh, here. Can you see hydroxide? OH minus. Here. Okay. Remember hydroxide. So hydroxide are things with OH minus. Okay. Yeah. Many pages ago. So when metals react with water, they will form metal hydroxide. Okay. With hydrogen. Yeah. Or metal oxide with hydrogen. Okay. Yeah. So I know you are confused. So write down an equation, please. So you have, for example, magnesium plus oxygen forming magnesium oxide. Yeah. You can have sodium. Remember that video I showed you about how what happens when we drop potassium or sodium into water? It explodes, right? You know why it blew up? There is hydrogen produced. Hydrogen is a flammable gas, meaning it can fire easily. Okay? So when sodium reacts with water, it forms sodium hydroxide. So you recognize the OH? Yeah? So why is this NaOH? Why not Na2OH? Why not NaOH2? Because Na is from group 1. What does being a member of group 1 mean? What is the charge of something from group 1? Positive 1. And from that table I just showed you, OH has a charge of -1. So tell me what you get when you do crisscross group. Do you have any number? Put as a substitute? No. So this is why it's NaOH. It should explain things. Okay? So it's not Na2OH, not NaOH2, but just NaOH because of this. And we have also hydrogen. So the hydrogen is the reason why it exploded. Okay, when you put it in water. Okay, let me show you that video again. Okay, so this one. So you have, when you have, so this is sodium. One every time. So loud. Okay. So it's hydrogen that causes it to explode. Okay, so this is why in chemistry we need to learn to write equation. We write equation to explain observation. Okay, so the hydrogen explains why. So you can say it's flammability. It catches fire easily. Okay, explain why sodium explodes in water. And it also explains why you're not allowed to do this experiment. Lemon is not on your home. Okay, it's dangerous. Okay, so what else? What other things can metals react with? Metals can also react with acid. Okay, so metals can react with acid to form salt and hydrogen. Okay, so you get metal salt plus hydrogen. So we call these salts. Do you remember what salts means in chemistry? We mentioned this a while ago. Salts in chemistry means what kind of compound? Is it ionic or covalent compound? Ionic compound, yeah. So don't misunderstand this word here. Salts in chemistry means ionic compound in general. It doesn't always mean table salt. Okay, so don't think that whenever I react with metal variants, I always get table salt. No. Depending on what metal you react, okay, with acid, you may not get table salt. Okay, so if you use sodium to react with the acid in your stomach, hydrochloric acid, yeah, then yes, you get table salt. But if you use other metals like magnesium to react with the stomach acid, okay, hydrochloric acid, you will not get table salt. You get another salt. It's magnesium chloride. So now, just to check that we are on the same page, can anyone explain to me why is the formula of NaCl, and the formula of MgCl2, MgCl? Why can't this be NaCl2 and why can't this be MgCl? Can you explain your answer based on the group numbers? If this is from group 1 and group 7, this is from group 2 and group 7. What are the charges? What are the charges of these ions respectively? Yes, this has 2 plus charge, this has a 1 plus charge, and Cl, because it's from group 7, it must have a 1 minus charge. So can you put this down please? So know how these formulas are to be used. So so write down the charges, and you have, so this will be part of the test. I tell you, the working of the formula, the prediction of the formula. So you must know how to predict the formula. So the charges in relation to the group number, you can find that table on a previous page. Okay, yeah, you can copy this first. And can I have some help balancing both of these equations? So 30 seconds. Or after you copy the equation, balance it. Remember, to balance an equation means to put an appropriate purple number in front of the chemicals. Okay, so we'll check the answer in 30 seconds. Yeah, so I need some numbers here, 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 and there. Okay, in both of these equations. They are known as what color? halide means chloride, bromide, iodide, fluoride. Okay, so halide means fluoride. Remember in toothpaste there's sodium fluoride. So fluoride is a halide. There is chloride in table salt, sodium chloride. Okay, so there may also be, do you all know what iodized salt means? Iodized salt.
It's
Yeah, they are salt with iodine infused. Okay, why do we need that? Have you seen a condition? Have you seen people with a swollen neck before?
goiter.
Yeah, I haven't seen one person like that in a while. Okay, but usually when you see one, it's pretty exaggerated. So this is a condition called goiter. It is caused by a deficiency in iodine. I'm not sure if any one of you here do not eat seafood. Maybe because of religious reason. Okay, there is seafood allowed. Yes, in all religions. Yeah, so but there are some people who just don't like eating seafood. I don't know why. And this is what happens if you don't eat absorb enough iodine. Why do I emphasize seafood? Because in seafood there is a lot of iodine. Okay, so without iodine, this is what happens to your neck. It swells. Okay, so we call this goiter, and this is why in the supermarket you will find iodized salt. So this is the remedy for those people who insist not to eat any seafood. Okay, you can use the iodized salt, so they at least get some iodine, so they don't get goiter. So iodized salt, you can say this is just something extra, but prevent goiter. You might want to. It's interesting. So you have fluoride, bromide, or iodide. This is a term that summarizes it all. Halide means these all four combined. So now write down an equation. When sodium reacts with the halogen chlorine, you can get sodium chloride. Okay, I have a video for this as well, which I think I showed you before. It's so just balance the equation first. 2Na plus Cl2 gives 2NaCl. Okay, now this video is about this guy trying to season like a pizza with what is that? With sodium chloride. So chlorine is here. So this person is this is sodium metal. He's melting the sodium metal with a torch, and then you can find on this label. So you can, I know it's very faint. You can see chlorine on this bottle. So he's letting chlorine to react with the sodium metal, and you see white smoke form. So there will be white smoke. The white smoke is actually table salt. Okay, so table salt. So he is going to fetch his pizza, and he will put his pizza next to those smoke because he wants to season the pizza with table salt. That's sodium chloride that is formed. Okay, so if you can read these words in here, it says the smoke is common coating salt. That's sodium chloride. So I want you to know that these reactions are really that useful. You can really use metal to make a lot of stuff, each with different applications. You can make salt when you react metal with halogen. You can also make salt when you react metal with acid. So these many things are what metals can react with. Okay, so that's number one. What you need to know. Yeah, and the lower the reactivity, the less reactive the metal gets. So therefore, I wrote down the word May. So magnesium, because it is high up in reactivity. So you see where is magnesium? Magnesium is here. So it is pretty high in reactivity. So it can react with oxygen. But this cannot be. This is not possible with lower reactivity metals like gold and silver. They are too unreactive. They will not react with oxygen at all. So therefore, I use the word May. Okay. And similarly, some metals, for a fact, it will not react with water. Like gold. When you drop gold into water, does it react? No. I mean, if it does, it will not cause so much, right? Because it will just like dissolve and yeah, it's bad. So, so this is why only metals high up in reactivity can react with these four substances. The lower the metal in the reactivity, the less reactive it gets. So next up, we have the order in which the metals are discovered and used. So the chronological. So chronological order, meaning the order in time. Okay, so chronological. So order in which the metals are discovered. So I'm not teaching you history, okay, but you may have heard of the Stone Age. Okay, so Stone Age is, of course, when we use stone, and also some metals like gold and silver. So can you put down the chronological order? This is the arrow of time. So we have present on the right, and we have past on the left. Okay, so this is the chronological order. We have the Stone Age first. What comes after Stone Age?
Bronze.
No, not so soon, not so soon.
Copper.
Copper Age, yeah. So we have Copper Age next. Then we have Bronze Age. And so all this happens before Christ. So BC. And then Anno Domini, we have the Iron Age. Okay, yeah, the Iron Age. Right, so let's put down what happened like in these different time in here. Not put down the exact time because that's not going to happen anyway. So just know that Stone Age comes first. So Stone Age is when we use stones and silver and gold. So silver and gold. That's because these metals don't need extraction at all. They are immediately available. Okay? And by the way, gold is not naturally formed in the earth. Right? You know, most of the elements, they are formed inside the earth's core, right? By a fusion effect. But gold is not made this way. Do you know where all the golds on earth come from?
Meteors.
Yeah, from meteors, from meteorites. Okay, they come from outer space. When supernova event happens, when those stars explode, they can form gold and silver. The earth, the core of the earth is not hot enough, not strong enough to fuse elements into gold and silver. So this is what makes gold so rare. Because they are not formed on earth itself. They come from meteorites. Okay? So use stones and silver and gold. So put down these metals, they don't need any extraction because they are already in the free unbound state. Okay, so already in free unbonded state. Then we have the Copper Age. So do you remember if copper is a very reactive or very unreactive metal? It's pretty unreactive. Okay, you see it's the second last, the third last metal, copper. So because copper, so we use copper. So copper, because it is not very reactive, although it is slightly more reactive than silver and gold. So this is easier to extract. So because of its low reactivity, when humans learn to use like a furnace, they learn to extract it. Okay, so therefore they are pretty easy to extract because of their low reactivity. So you know when you are not very reactive, it means you do not bond to oxygen as tightly. Okay, so imagine copper as like a person. Being not very reactive a metal means it is holding onto oxygen just very, very loosely. So therefore, you can easily come around and pull the oxygen away from it easily. So that's what being not very reactive means. Okay, if this is not very reactive, it means it doesn't pull on oxygen very tightly. It doesn't attract it very tightly. So therefore, it is possible for you to take the oxygen out very easily. Okay, so you can put down because this is not very reactive metal, so not very reactive. Therefore, so not very reactive. Therefore, okay, point number 2. Copper does not attract oxygen strongly. So what's the consequence? The consequence is, therefore, it is easy to extract one that is made from copper and zinc is brass. Okay, so just put this down. So we have copper and tin for bronze. Copper plus zinc is brass. But both of these, they have one thing in common. They are alloy. And humans only learn to make alloys in pretty recent times. Okay, so this is why Bronze Age comes after Copper Age. Okay, so right now alloys, they are stronger. So therefore, yeah, we learn to build like stuff that are stronger. We learn how to weld, weld swords. Okay, like yeah, make swords and stuff. So we'll pick up from here next time. And first stage test. Okay, remember to review the formula. Okay, the making of formula. Okay, so remember to revise this first stage and this first stage. Okay, so let me upload this. Yeah, and default is that now.